Here is a question that sounds simple but is not. What is an algorithm actually about? Take the old Russian peasant method for raising a number to a power. Point it at ordinary integers and it computes powers. Point it at a 2 by 2 matrix and it computes Fibonacci numbers. Point it at a rotation and it composes turns in space. Point it at a graph and it finds shortest paths. The code never changes. Only the thing it runs on does. So the algorithm is not really about numbers or matrices or graphs. It is about something all of them quietly share. That something is algebraic structure. And it is the single idea this whole series is built on. The idea comes from Alexander Stepanov, the designer of the C++ standard template library and the author of Elements of Programming and From Mathematics to Generic Programming. Stepanov spent a career on a single conviction, that algorithms are not tied to particular data types. They are consequences of algebraic structure. His central insight is this. The algebraic structure of a type determines which algorithms apply to it. Tell me the operations your type supports and the laws those operations obey, and I can tell you which algorithms come for free. You do not invent them. You discover that they were already there, waiting inside the structure. This flips the usual way we program. Normally, we start with a problem and write an algorithm for it. Here we start with structure. Declare that your type is a monoid, an associative operation with an identity, and you immediately get power by squaring, fold, and parallel reduction for free. Declare a semhering, and the very same matrix power code gives you shortest paths, reachability, and path counting, depending only on which two operations you provide. The lesson runs backward from habit. Do not start with the algorithm. Start with the structure. See the structure first, and the algorithm follows. This series climbs a ladder of structures, and at each rung an algorithm falls out. Monoids give us exponentiation, Fibonacci, and rotation. Euclidean domains give us the greatest common divisor, for integers and polynomials alike. Rings, extended with a single infinitesimal, give us automatic differentiation, the engine behind modern machine learning. Semherings turn one matrix power into half a dozen classical graph algorithms. Higher up, homomorphisms, the structure-preserving maps, explain why fold works on any monoid and why it parallelizes. Free algebras explain why lists and polynomials show up everywhere in programming. And lattices, with Tarski's fixed-point theorem, give a single convergent iteration that underlies program analysis. Different structures every time, but always the same move. Name the structure and derive the algorithm. Each episode builds one structure from scratch, in about 200 lines of pedagogical C++, and then derives the algorithm that the structure implies. The code reads like a textbook that happens to compile. One idea applied over and over until you cannot unsee it. Algorithms arise from algebraic structure. Let us begin.